So the first type of force we talked about was the force of gravity. How do we know, how are we going to be able to tell if gravity is present in a situation? Anybody?
I think if it is going down or up.
Well, gravity is, well, that's not necessarily how we know if gravity is present, right? If I'm sitting here at my desk and I'm not moving, does that mean that there's no force of gravity on me?
Since we're in Earth, there's always gravity, no?
Yeah, there you go. That's good. Since we're on the planet of we're on Earth, we can feel the Earth's gravitational pull always. So this first one's pretty easy. How do we know if there's going to be gravity on our free body diagram? Well, there always is. All right, so you're always going to have gravity on your free body diagrams unless you're not on the Earth or another planet. So as long as we're near the Earth. Or some other planet. Or star or moon or whatever. All right, but we're always going to have the force of gravity. And when we put the force of gravity on a free body diagram, what direction are we going to make gravity point?
I mean, it pulls us down, doesn't it?
Yeah, exactly. Gravity pulls us down, right? So that means the force of gravity is pointing downwards. So that's always going to be a down arrow, right? And that's because it's towards the center of the Earth. Gravity pulls us towards the center of these big objects like planets. All right, so when we're looking at our free body diagrams, first thing to ask ourselves, is there going to be gravity? And the answer is almost always going to be yes. So we put a down arrow on the free body diagram for the force of gravity. Okay? And again, stop me if you have any questions or anything. The next force we learned about was the normal force. How do we know if the normal force is present in a situation? We saw it briefly in the notes the other day.
It's if the object is on a surface.
Right. Yeah, so if the object is sitting on a surface, right, so on a floor, on a table, or on something else, then there's going to be a normal force. Right, so the only time it wouldn't be on an object wouldn't be on a surface is maybe it's, you know, flying through the air or something like that. So I'll put in parentheses, so not in the air. All right, so if the object is not on a surface, then you wouldn't put the normal force arrow on it. But if it is on a surface, you do need the normal force. And what direction, anybody have any ideas on what direction we would draw the normal force arrow?
Upwards?
It's usually going to be upwards, right? If you're on a flat surface, then the normal force is going to be upwards. But if you're on a slant, it's a little different. It's actually perpendicular to the surface. Right, which is normally going to be up. I'll put upwards for a flat surface. All right. So as we're going through these exercise examples, you can ask yourself, is this object, you know, on the ground or on a surface? And if it is, you're going to want to make sure that you have the normal force. Okay, the next type of force is the force of friction. And how are we going to know if the force of friction is present? This one's a
When we feel pressure?
when you feel, yeah, that's getting pretty close to it. Yeah, there's got to be some pressure between the object and the surface that it's on. and we didn't really mention this much in the notes the other day, but if it's on a surface and it's sliding along, or if it's trying to, then there's going to be a force of friction. All right, so I'll put that the object is sliding along a surface. Or is trying to. All right, so if the object's sliding along a surface or it's trying to, then there's going to be friction there. And if it's not on a surface, like the normal force, there won't be any friction. And the friction for the direction, does anybody know what, I think we mentioned this in the notes the other day, anybody know what direction the force of friction is going to be?
Opposite.
Right. It's going to be opposite to the direction of motion. Right. Friction always wants to resist the motion, so it always pushes in the opposite direction of the opposite direction to the direction of motion. So if I'm sliding to the right along the floor or something, then the force of friction would be to the left, and it's going to tend to slow me down and bring me to a stop. Or if the object's not moving but it's trying to, then it's opposite to the direction that the object's trying to move. All right, so far? Next, we've got the applied force. Do you remember what the applied force is, or what an applied force is? There's kind of a lot of different types of applied force.
So it's like if you push or you pull something.
Yeah. Yeah, I mean, and well, that's true. All forces are really a push or a pull, right? But an applied force is when there's somebody or something that's there directly pushing or pulling on the object. Right, so I usually think of it as someone or something that's exerting the force. So they're directly pulling or pushing the object. And the direction for that is just whatever direction the push or the pull is, right? You can push or pull something in any direction you want, and that's the direction that the arrow should go in the free body diagram. So I'll just put the direction of the push or the pull. All right. So those are the four types that we talked about the other day, and put those into our notes. I want to go over a couple more types of forces because because you'll see them on the example today, and they're not really new types of forces; they're just kind of subtypes. So we have mentioned air resistance before when we were talking about free fall. So let me mention air resistance, the force from the air. And it's important to know about air resistance. It's just a type of friction. Right? Air resistance or wind. You can think about if you're on a windy day, or if you're running and you can feel the wind in your face, or if you're falling and you feel the wind. Right? That's air resistance. That's the air molecules rubbing against you and trying to slow you down. So the force of air or force of air resistance is a type of friction. And the way we can tell if it's present is if the object is moving through some air. And you can be on a surface or not to move through the air. You just have to be moving and there has to be air around.
Yes, sir. So
Yeah.
an example of this would be like a balloon in the air.
You broke up, I couldn't hear you. Could you ask again?
So I just said that like an example of this would be like a balloon floating in the air, right?
Yeah, so right, the reason the balloon doesn't kind of fall down to the earth like a rock does is because there's a lot of air resistance on the balloon because it's pretty big but it's very light, so the air resistance is pretty close to the amount of gravity. Yeah. Okay, Danilo, that's fine. Okay. A lot of times though, and there's almost always going to be air resistance, but for a heavier object, a lot of times air resistance we can ignore. So sometimes we'll be able to ignore it, and if you read the problem, you'll see, we can ignore air resistance, or air resistance is negligible. That all means don't worry about air resistance. So I'm going to put in here, often we can ignore air resistance. And since it's a type of friction, it's also opposite to the direction of motion, right? If you're falling downwards, you can feel the wind blowing upwards at you, right? If you're running, northwards along the street, it's going to feel like the wind is blowing to the south. So opposite to the direction of motion again. All right. And then there's one more type that I want to go over with you. It's a type of applied force. It's really no different than any other applied force, except we call it something different: tension, force of tension. Anybody know what the force of tension, what I mean by that? It's a type of applied force.
When you kind of like pulling like a rope or something like that.
Yeah, exactly, right. A tension is an applied force that's when you're pulling something along with a rope or a string or a cable or something like that. So it's just an applied force using a rope or a string, and we say that there's tension in the string or tension in the rope, right? You can imagine a rope being real tight because it's pulling hard on something. There's a lot of tension, and then if you kind of let it go, the tension goes away and it gets real slack, right? So we'll call if you call a force from a rope or a string an applied force, you wouldn't be wrong, but we also call it tension. So a rope, a string, or a cable, anything like that is directly pulling the object. So it's just an applied force, but with a rope or string. And just like applied force, the direction is just the direction that you're pulling. Okay. Any questions about those types of forces, or how we know if they're present or what direction they're going to be? All right, so before you get started on your assignment for today, I'm going to go and do one of the examples with you. So I'm going to stop sharing the paper now, and if you need to, remember on Google Classroom, this table is there for you to reference. So that's there. All right, so when you get to the assignment for today, and let me see if I can find it. Here it is. This is the assignment for today. There's 3 links there. There's first 2 links are informational. This types of forces one basically goes over exactly what we just did together. So that if you're stuck, that would be a good thing to take a look at. And this drawing free body diagrams link, that gives you some examples of a couple just like that you're about to do. So if you are stuck or struggling, it would be great to take a look at those. Right, those should be the first 2 resources you use if you're stuck. This third link goes to the interactive itself. So I'm going to do one with you. We'll make it full screen. And there's 12 different situations, and it gives them to you in a random order, so I don't know which one I'm going to get. Hopefully it'll be a good one to start with. So let's go with situation 1. And your situation 1 won't be the same as my situation 1. Okay. So here we go. Let me try a different one. Okay. So it looks like a good one to start. This one says the cabin of a small freight elevator is secured to a motor by a cable and is moving upwards while slowing down. There's no contact between the cabin and the elevator shaft. Ignore air resistance. All right, and so it's our job to draw the free body diagram of this situation. And the way to do that, right, don't just start putting arrows in every direction because there might not be an arrow in every direction. We go through force by force, these 6 types of forces that we just talked about. So the first one was the force of gravity, which we said was always present, right? We're on this elevator, I assume, is on Earth. So, and I know gravity's always got to be down, so I can assume I have a down arrow. That's the force of gravity. So I'll click down, and I'll pick gravity. Gravity's always there. That's the easy one. The next force on my list is the normal force. Is there going to be a normal force on the elevator? What do you think? Sorry, was it Eric? One more time. Yeah, there is. Okay, there is going to be tension, but let's go one by one because we don't want to miss any. So normal force is the force of an object that's sitting on a surface. Is an elevator that's being pulled upwards by a cable sitting on a surface?
No.
No, right? So no normal force. All right, so I'm not going to put a normal force on this one because it's not on a surface. What about the force of friction? Is the elevator sliding along a surface or trying to?
I don't think so.
No, it's not, right? It's being pulled upwards by a cable, by a rope. So there's not going to be any friction there. So we don't have to put a friction arrow, right? If it was sliding along a surface, we would put a friction arrow. What about applied force? Is there an applied force here? Is someone or something pulling on the elevator?
Yes,
Yeah, there is. And what's doing that?
the machines. I don't know, the machines, I think.
You're right. There's machinery in the elevator, right? That pulls upwards on the cable that's attached to the elevator, right? That's how it works. So there is an applied force. And what direction is that going to be?
Up and down.
Well, which one? Which way is it pulled? Up, right? It's being pulled upwards. So that the applied force are really, well, yeah, it's being pulled upwards by that cable. So I could put applied force and I wouldn't be wrong, but this is going to tell me I'm wrong because there's a better name for that type of force than just applied force. Right? It's being pulled upwards by a cable, so I don't want to just call it applied force. What do I call an applied force that's using a rope or a string or a cable? Tension, right? So I'm going to call my upwards force tension. All right, now I'm getting through these, right? I only have air resistance to look at next, right? And the very last sentence here, ignore air resistance. Well, that tells me I don't have to put air resistance on my free body diagram. Right, and then the last force on the list is the force of tension, and we already put that on there. So those are all the forces I have on there. So I might think I'm done, and I can click check and see if I'm right. And it says my free body diagram is not correct. And it's going to give you a hint, so make sure you read if you get something that's not right. It says the force types that I've chosen are correct, so having tension and gravity is right, but the errors pertain to the size of your forces. So if I look here, it says the cable is moving upwards, but it's slowing down. Right? If it was moving at a constant speed, then I would know it's in equilibrium and my tension and my gravity would be the same length. But I know it's moving upwards and it's slowing down. So I have to make one of these arrows bigger than the other one. So if I'm moving upwards, what direction does the stronger pull have to be to slow me down? Would a bigger upwards pull slow me down, or would a bigger downwards pull slow me down?
Bigger downwards.
Bigger downwards pull, right? If I'm moving upwards and you want to slow me down, you've got to pull downwards harder than the upwards pull. So the downwards arrow should be longer, and you can click on these arrows to change their size. So if I click on it, see how it goes back and forth. I want to leave it the force of gravity longer than the force of tension. That's going to make it slow down on the way up. And now I check my answer. This time it tells me I'm right. So I would take a screenshot of this, and once you've got, you know, kind of the way this works is you got to kind of collect the screenshots, right? Each one you get right, take a screenshot, and then submit that to the assignment when you're done.